We are fine. Okay, so we are ready.
All right. Good evening, everybody. Welcome. Welcome to the first active class. So the topic of today's session is embeddings and transformers. But before we get into the topic of tonight, I just want to touch upon a few housekeeping items. I put out a introduction video to the course a couple of days ago. So if you haven't seen it, please go ahead and watch it as soon as you can. So the goal of the first introduction video is to introduce the syllabus and talk about a few important dates. One quick thing about the introduction video, there's a small mistake in it. I say that the master class is on the 25th of August, but it's not on the 25th, it's on the 22nd. So just always be sure to check in the calendar for the important dates. And another quick comment is that um, if you start a quiz, be sure that you're ready to take the quiz. So some of you have already tried to open the quiz before today's session, and we'll make an exception for those. But in the upcoming weeks, if you start taking a quiz, make sure that you have reviewed the study resources and that you have reviewed the content of the active class that came before the quiz before you start taking those. So I think we're about 60 people in the class, so that's a good amount. I have the chat open on another screen. I do encourage you to post questions. If you're not too shy, you can also ask your questions verbally, of course. Um, so I'll do my best to answer as we go. The topic that we're going to see today is going to cover what you need to understand from a theoretical perspective for module 1 and 2. Of course, there's other resources that you're going to get access to on the canvas. So without further ado, let's begin with today's topic, embeddings and transformers. So one thing I like to start with is with this slide. So I like to introduce foundation models because I think it covers really well the whole course that we're going to see in the next 6 weeks. And I think it explains really well why this topic is so important and why we have seen such a transition in the last year or two in the AI space. And I like to compare what I like to call old paradigm versus the new paradigm. Um, I started working in AI about like 8 years ago. And back in those days, I was working for a financial institution and I was working as a senior scientist. And in those days, we were in the old paradigm. And what I mean by that is every single time we had a business problem that we wanted to solve, it meant that we had to acquire the data for this specific problem, and we needed to train a specific model to solve that problem. So every business problem had its own data set, its own problem, its own model, sorry. And if you think about it, that can be very time consuming to acquire the data, clean it, train the model. And if you have good results with that model, you need to maintain also this model once you start using it in a business context. So that's what I try to illustrate with this diagram is every problem has its own data set versus how things have evolved nowadays with foundation models is if we take one of the most notorious foundation models, that would be ChatGPT, right? So that's a LLM, large language model. It's part of the generative AI category of models. But there's so many other types of foundation models like DALI, and you have many foundation models that are for images or for time series. But what's special about this category of models is that they are trained to address many different business problems. So you have one model and you can do so many things with it. And of course, if you have a little bit of data, what you can do is take your foundation model and you can tune it and adapt it to that business case. But very often, that's not even required. You can just use a model that is off the shelf, like GPT, and you can do so many things with it. And another component of foundation models is that you can prompt them. You can give them instructions so that they perform in a very specific way. Some of the advantages of foundation models is that the performance is like nothing we have seen in the last 10 years. And that's why they have been so transformative. In terms of productivity, that's also a big bonus because, again, if you compare the old paradigm versus the new paradigm, you have one model that you use for so many different things, right? So you don't waste time training and cleaning the data, and that process of maintenance is a lot easier. Some of the disadvantages would be the compute time. So again, if we want to give some concrete examples of foundation models, that would be Claude from Anthropics, GPT, Mistral, Gemini. There's so many that came out in the last 2 years. But for most organizations, training a foundation model is, I don't want to say impossible, but it's so expensive. If, for example, the company that I work for right now, which is a 2000 plus employee company with lots of resources, if we wanted to train our own foundation models, we would need to spend a lot of money on just GPUs and compute time. So that's a big disadvantages of those models. But luckily, it's very easy nowadays to just buy access to models like GPT. Anybody can do it. Another disadvantage of foundation model is the trust aspect. There are things that we can do to work around the trust issue, and we're going to talk a little bit more about that in future sessions and in this course in general. So, with that being said, some of the basic concepts around foundation models, from a theory perspective, again, would be this concept of encoding and decoding inputs or information in general. We're going to talk about this in a few moments. Encoding and decoding is really a key aspect behind transformers and behind embeddings. So today's session is really about those three topics: encoder, decoder, transformer, and embeddings. And then the idea of transformer learning is what I just explained. So you have one model that does many, many things. So you can transfer the knowledge of that model to many different scenarios. Let's talk about autoencoders. Autoencoders is a topic that I cannot seem to stop covering whenever I teach embeddings and transformers. It's a very, I don't want to say it's an old model, but it's something that dates from many years ago, but the theory behind encoders or autoencoders still lives today. And let's just go over the basic architecture of an autoencoder. An autoencoder is a neural network, but it's a very specific type of autoencoder. I see that there's a question. Okay, so it's a question about a book for the class. So in terms of books for the class, there isn't really anything that's been specified in the study resources, but there's a lot of articles and a lot of YouTube videos that are suggested. Well, not suggested, that are required to read and consult for the sessions. So going back to the architecture of neural networks and autoencoders, so if we take a very vanilla looking neural network, what you'll have is you'll have inputs uh, that we can just call X for now, that are going to go into your neural network. And what you have in your neural network is a series of hidden layers, right? And what you're trying to do is you're trying to predict a variable y. So, for example, if we take a very classic finance business case, it would be like, let's say I'm trying to predict um, the return of an investment in the next week. Let's say I want to predict the return of Apple, which is a company, in the next week. So maybe what variables I would be using for that would be the returns that they had in the last year, maybe the revenue, the growth. So I could try to get as many inputs or information on Apple, and I would try to infer the return of Apple in the next week or so. So a classic vanilla neural network is always mapping some inputs X to a variable Y. If we compare that to an autoencoder, it's very different. Okay, so an autoencoder, if we want to really simplify the architecture, it looks like what you see on the right, and there's three main components to it. The first part is what we call the encoder, and the encoder is going to take the input X, it's going to squeeze or compress all of the information into a smaller dimension, which is what we call the Z variable or the latent representation. And then the second part, or the third part, I should say, of the autoencoder is what we call the decoder. So it's going to take the latent representation and it's going to expand it back into X's original size. So it's a very unique and odd architecture because what you're trying to do is you're mapping X to X, right? So I'm going to pause here for just for you to reflect on this. Why would we want to map X to X is the question that you should be asking yourself. Why do we care about squeezing inputs into a smaller dimension and then expanding it back into its original size? I'm looking at the chat and somebody suggested attention is all you need. It's a great article to read. So I see there's a hand raised, so don't be shy, ask your question.
Hi. I think it would be to compress information and then decompress it.
Yeah. So the answer I'm looking for in when I say why do we do this is that the Z variable is really what we care about. This vector here, right? Because what we're trying to do is we're taking an input. Sorry, we're taking an input and we're reducing the dimensionality just like you would do with a PCA. And what you end up with in this Z vector is a richer, more condensed version of X. So it's a version of X, but without any noise. You're removing all the information that is not important, basically. And autoencoders are used to extract meaningful features. And it's the same idea that you would have in a transformer and in embeddings, which we're going to see in the next couple of slides. But thank you for asking the first question of today's session. Okay, so just to illustrate the concept of autoencoders, let's say that you have a handwritten digit that is a 2, which is what I put on the slide here. And what I did is I added some noise to the image. Okay, so this is noise, this is noise. So if I ask everybody in the class today to write on a piece of paper a 2 and then take a picture and submit it into the chat, everybody's going to have a different 2. But unless you have really bad handwriting, we should be able to tell that you wrote a 2. Why? Because there's a pattern to a 2. You know, you have like this round shape, it goes to the corner and then horizontally to the other corner. The black spots here, it's just noise. It's not what makes this a 2 a 2. So if we take all the handwritten 2s of everybody in the class right now, and we train an autoencoder with it, what's going to happen is if you take an image of a 2, you pass it through the autoencoder, you'll get another 2 at the end, but the 2 will not have any noise. So these spots will disappear because it's just noise. It's not relevant information. It's not what makes this a 2 a 2. So another question I would ask you guys is the funnel shape of the autoencoder is really important, right? So what I mean by funnel is that you have an input and all of the hidden layers in the neural network, it gets smaller, right? So every hidden layer has a smaller dimension and smaller dimension. And then in the decoder part, it should be like the mirror of the encoder. If we had an architecture that looks a little bit more like what you see on the left, where you have every hidden layer has a dimension bigger than X or the same, what do you think would happen?
You don't actually reduce the noise.
Yeah. Or you are not compressing also could be, right? Like you're
Exactly.
having the same elements.
Exactly. You wouldn't really learn any meaningful features because it would be very easy for the network to just pass every input all the way to the end. It would replicate perfectly the input, but it wouldn't really learn anything that is meaningful. So that funnel shape is really important. Okay, so that was just the introduction of the concept of encoding versus decoding stuff. Now let's get into embeddings. Not sure if you guys have ever worked with embeddings in the past, but if you haven't, so embeddings is a way to represent words, sentences, or text, language in general, into a numerical format, right? Why do we want embeddings? We need embeddings because machines don't understand human language. So if you have a sentence like, I love learning about artificial intelligence, a machine or a model does not understand that. It does understand numbers. So we need to figure out a way to take language and translate it to numbers so that we can use models, so that models can use language. So the question becomes, how do we do that? Before we had embeddings, we had some more simplistic ways of encoding text. Some of the most old school, if we can say that, would be one-hot encoding and count-based representations. So let's talk a little bit about these two older versions of of converting text to numerical formats. One-hot encoding is this idea where if you have a vocabulary, it's a very small vocabulary. We have 8 words: machine, language, data, model, word encoder, and learning, and attention. So with one-hot encoding, the way this would work is you would have a vector that is as long as your vocabulary, And every word would be represented by one vector, and this vector would contain only zeros, except in one area, and that would be the spot of your word. So if you have the word model, you would have 0, 0, 0, 1, and then the rest would be 0. So, okay, that's a very easy way to represent words. But what happens is if you have a very extensive vocabulary, like thousands and thousands of words, then that means that you have a very sparse vector and there's only one value in that entire vector that contains a 1. So it becomes very inefficient to train and just to represent your language in general. Count-based representation. So there's many count-based representations of text. One of them, one simplistic way is to say, okay, I'm going to try to squeeze a whole sentence into one vector. And let's say I have this sentence here. I love learning about artificial intelligence, and I especially enjoy learning about transformers. So you could say, okay, I'm going to put a 2 for the word about because I have about that comes twice in the sentence. I have artificial once in my sentence, so I'm going to put 1 here, and then I have I twice. I'm going to put a 2, and so on. So it's a little bit more efficient because you're squeezing the whole sentence into one vector, but it's still going to be very sparse. And you also lose track of the order of the words in this sentence. Some other forms of count-based representations would include bag of words, engrams, TF-IDF, but they all have the same issue. And the main one for me, or not for me, but the reason why embeddings are so much more powerful than the count-based representations is that the count-based representations do not incorporate context. So it's just a way to represent a word, but you don't understand the whole context of the sentences or the paragraphs around that word or around that sentence. So it's missing a lot of the key information. The other issue is that you can't really deal with unknown words, right? Every time you have a new word in your vocabulary, then you need to change your representation. And as I said before, you're going to end up with very sparse vectors, so very inefficient to train in a neural network. So that would be the definition of embeddings. So embeddings, they aim to represent the words in a dense vector. Dense meaning that you don't have a lot of zeros. Okay, so every value in your vector should have a value that is not 0. And you want to make sure that similar words are close to one another in your embedding space. So let's do 2 very small examples of how you would represent words in a 1-dimensional and a 2-dimensional space. So let's say you have 3 words. You have coffee, you have tea, you have pea. T and P, they kind of look the same, but they don't mean the same thing. Coffee and tea, on the other hand, they're spelled very differently, but they would be used in a very similar context. So coffee and tea are things that are going to be associated with breakfast, drinking, enjoying your coffee, enjoying your tea. So you would expect if you take your embedding space and you embed all of these words, what you would expect is to have a smaller distance between the word coffee and tea than between the word tea and pea. So that's one thing we would expect from an embedding model. Let's take the 1-dimensional space. Obviously, a 1-dimensional embedding model would be a very terrible model in real life, but it's just to illustrate the idea. So again, let's say we have a very small vocabulary. We have machine, language, data model, word, encoder, learning, and attention. So every word is represented by one number. Machine is 3, language 11, and so on. So if you want to map that in one dimensional, it would just be a flat line, right? So you have one dimension from 1 to 13 in this case, and word would be here in the dimensional space, model would be at 13, and every other word in between. So now if we want to compute the distance between two words, for instance, if we want to compute the distance between encoder and data, we would do 9 minus 5, and that would be 4. And if we wanted to compute the distance between attention and learning, it would be 7 minus 6, that would be 1. So the interpretation in this one-dimensional embedding space is that attention and learning would be closer. They are closer in the embedding space, so they are more similar than encoder and data. Obviously, this is just a random example, but just it's just to illustrate how words can be connected to one another in an embedding space. In the two-dimensional space would be a little bit similar, but it's just that instead of having just every word has a one number that represents them, they would have two numbers that represents them. So we can map them in this two-dimensional graph. So if we want to take perhaps another example in these words, you would see, let's say you have words like king, queen, prince, princess, kingdom, and then you have another set of words that would be birds, cats, cows. What you would expect in a two-dimensional space is that you would have all the words that relate to kings and queens in one cluster. And then you would have another cluster for all the words that are talking about animals, that are referring to animals. Okay, so you would start seeing some clusters of information in your embedding space. Now, in real life, if we take embedding models like GPT and OpenAI's embedding models, they have thousands of dimensions. Okay, so it's not possible to represent them in a visual format, but it does give you an idea of how it works. Okay, so let's go through a round of questions. The goal of these questions is just to recap what we just talked about. You can answer in the chat what you think the answer is. So the first question is, what is the advantage of using word embeddings over traditional one-hot encoding for words? You can post your answer in the chat. Lots of B's, all B's. Yeah, so word embeddings capture semantic relationships between words. Second question is, how can word embeddings be used? Is it for sentiment analysis? Is it for text classification? Is it for machine translation? It's kind of a trick question. Yeah, so it's all of the above and more than all of the above. Anytime you have text, you're using embeddings, basically. So that brings me to the next topic, which is transformers. Okay. We have, I didn't mention it at the beginning, but we have about 50 minutes to an hour of theory. And then the last 30 minutes, I really want to save it for to go over a tutorial where I show you some code of how to use embeddings, how to use transformers. So we have about like 20 to 30 minutes left of theory. I see that there's a hand raised. So if you want to ask a question, go ahead.
Yeah, probably it's me. Yeah, it's me. Just a quick question about embeddings.
Yeah.
how these distances are calculated. Like we are going to put all these vectors like in some kind of neural network or something like that.
No, it's actually much simpler than that. There's
Oh,
many ways that you can compute a distance. So if you have a vector, right,
mhm.
you can compute a similarity like a cosine similarity, or there's so many metrics that exist to compute the distance. You have the Euclidean distance, you have the Manhattan distance.
Okay.
It's actually mathematically a lot simpler. You don't need neural networks to evaluate the distance between two vectors.
Okay, but those distances, like, how are they defined? Like, for example, how do we create these vectors? The numbers inside the vectors.
Yeah. I think the transformers is going to answer your
Oh,
question. Yeah,
okay. Thank you.
yeah, sure. Okay, so quick introduction to transformers. The architecture of a transformer looks like this. We'll go through the different parts of the transformer at a very high level. Okay, so this course is not meant to be super technical and super theoretical. It's really meant to be practical. Okay, so you're going to see that in the summer course, the emphasis is really on you applying the concepts to real data and you coding as much as possible. But I am touching on the different components of the transformer. If you want to have more details, I think somebody mentioned it at the beginning. Go read the article, Attention is All You Need, and you'll have like all the nitty-gritty details of the architecture. But in a nutshell, it looks a little bit like this. And transformers came around, I think it was in 2018 or 19. Before that, we had something called LSTMs, long short-term memory. And then before that, we had something called RNNs, recurrent neural networks. The reason why transformers have been so transformative is because they use this concept of attention, which we're going to see in a moment. And there's no recurrence to these models, which is an issue that we had with RNNs and LSTMs. And they are easy to train in parallel, which is something that you couldn't do with RNNs and LSTMs. So they are a lot faster to train. So they are overall, they have a lot of advantages over the predecessors of these models. So talking about attention, what exactly is it? Um, so if you have okay, so let me talk a little bit about this matrix that you see here. This matrix is where the transformer model is paying attention when it's trying to translate a sentence from English to French. So let's say that you have a transformer that's trying to translate the sentence, the agreement on the European Economic Area was signed in August 1992 to French. Okay, so I'll say it in French. L'accord sur la zone économique européenne a été signé en août 92. Obviously, I don't expect you to speak French, but this might be the same thing in Spanish, where in English you say European Economic Area, but in French, the words are reversed. So it's Zone économique européenne. And when you're trying to train models that do translation, they cannot just translate words literally. Otherwise, the sentences that you're going to end up with are not going to make sense, right? The order in which words are used is very important. So going back to the matrix, the transformer, when it's trying to translate the sentence in English to French, you'll see that when it comes to the word European, it's paying attention to two words in French, économique and européen. And when it's looking to translate economic, it's paying attention to zone and economic at the same time. And same thing for area, which in French it would be zone. It's paying attention to la and zone. So it's kind of being aware of this idea that when you're converting language to another, words don't necessarily come in the same order, and you need to pay attention to the whole context of the sentence. So that's one proof of how transformers have the ability to pay attention to specific parts in a sentence or specific parts in an image or a data point. Another example that I really like to illustrate how attention works is, let's say you have two images of different birds. So here you have what is called a Bohemian waxwing, and here you have a cedar waxwing. I'm not a bird expert, but I'm pretty sure if we were to show these images to a bird expert and we were to ask this person, can you teach us, can you explain to us how to differentiate the two? This person would say something like, okay, let's just focus on the head or the face of the bird. So if we zoom on this area, so we have the red squares over here, now it becomes a little bit clearer that these birds are different, because for the Bohemian waxwing, you have some red spots above the eye, you have like a little bit of orange at the bottom, whereas for the cedar, it's just, this black area with a little bit of white. And same thing for the tail and for the wing. You have red, you have yellow, you have black, you have white, whereas for the cedar, it's just black and gray. So it's really this ability of the model to identify which parts of the model, which part of the input matters for the task that I need to do. And when you think about it, that's how we think as humans too. So if you're trying to train yourself at a specific task, in this case would be recognizing birds, you're going to pay attention to specific areas of the birds to address the task. Any questions at this point? Okay. So what's the relationship between embeddings and transformers? So what I did here is I took the architecture and I just flipped it to the side. Okay. And for the next couple of slides, we're going to simplify the architecture. Let's just say that we have an encoder part and a decoder part, just like with an autoencoder. And let's say that the task that we want to solve is we want to be able to translate from French to English. So the way this would go is you would have first the sentence, the whole sentence that you want to translate. This one is really short. I love learning, but it could be a lot longer. This would go in your transformer. The whole sentence would go in the encoder part, and the output of your encoder would be a numerical version of the sentence, I love learning. So the output of your encoder is where all of the meaning of the whole sentence, that's really the key element. It's just not one word, it's the whole sentence that you're embedding into a matrix or a numerical format. Then the next step is every single time that you're trying to translate, but you're going to translate one word at a time. Okay, so the first sort of word is the beginning of your sentence. So it's whatever comes before the first word. And what you're expecting out of your decoder is to predict the word je in French, which is I in English. But in order for your decoder to translate or to predict the next word, the first word, je, it has the whole sentence in English, the whole meaning of it that is embedded in this numerical format. So the input to your decoder is the whole meaning as well as the first token that you want to predict, which is the start token. Once you have predicted correctly, or your decoder has predicted correctly the first word in French, je, then the next word begins. Okay, so in order to predict the next word, you're going to give it again the whole sentence in English that contains the whole meaning, along with the first word that it just predicted, je. So it's kind of like you're saying, oh, okay, so I love learning is what I want you to predict. I want you to translate. You just predicted je. Now, what comes after je? And then it should predict m. And then you're like, okay, you're on the right track. So again, here's the whole context. I love learning in English. You predicted j'aime, je and m. What's the last word? And then you would expect it to predict apprendre, which is learning in French. Okay, so I don't know how familiar you are with models like GPT, but I would expect that some of you have at least tried GPT or ChatGPT, right? So the way these models work is that they are trained to predict the next word. Okay, the whole internet was scraped, and these models are trained to always predict the next word. How do we do that exactly? Well, we pass it always the first word, and then at the beginning, when you instantiate your architecture of a transformer, the transformer is really bad at the beginning of training, so you just instantiate all of the weights in your neural network, in your transformer, at random. So all the connections in your transformer don't really mean anything. But as soon as you start training it, so you pass it the whole internet again. So you pass it one word, predict the next. At the beginning, it's going to be terrible. It's not going to give you good results, but the more you train it, the more the weights inside of your neural network start to optimize. Okay, so at a high level, again, the point of doing this small exercise was to illustrate how a transformer has, again, two parts, encoder, decoder, and each of those parts have a clear task at hand. The encoder's part is to learn the context because you pass it the whole sentence. So in this specific task, it really learns English in a nutshell. It learns the whole context in the sentence. Whereas the decoder part learns this specific task that you give it, which in this case was translating English to French. So it learns to map English to French words. Any questions so far? Yeah, I see that there's a hand raised.
Just just to be sure that I'm getting the correct idea, it would be the same if I put, for example, returning to the example that I love learning, I should be the first token, and then love, it will be like the I plus the love, and that's going to be translated one more time. And for last, it's going to translate the whole sentence, right? Until it's finished. So it's going to run the process 3 times or the n times until it get the complete sentence.
Yeah, so the decoder part is one word at a time, but the encoder part is the whole sentence at once. And that's important because if you're only passing one word at a time to your encoder, it does not learn the surrounding meaning of the sentence. So I alone, what does that mean? Love alone, what does that mean? And learning alone, what does that mean? But I love learning is a whole context. So going back to what you were saying, I love learning gets sort of embedded all at once, but then the generation part of the translation of each word is one at a time.
Okay, perfect. Thanks.
Sure. I see that there's another hand raised.
Yes, thank you. Just one question. So in the encoder part, it happens the dimensionality of each of the whole sentence, and after that, it goes to the part of the decoder. Is that like how it works?
Yeah. Yeah,
Okay.
exactly. So if you think about like this is the translation example, but if you go, for example, to ChatGPT, right, and you ask a question like, give me a summary of my essay, and then you copy and paste your long essay of like 50 pages. So it has the whole context. It'll take your entire essay along with your instruction, and that's going to be embedded into the whole context, like this sort of matrix. And then it's going to start generating the summary of your essay. But while it's generating every word of the summary, it has the whole essay. It has everything in context, always. That's
Okay.
how it's able to take the instruction along with the entire context of your essay and produce something that is of a shorter version.
Okay. Okay. Thank you.
Sure.
There's a question also in the chat.
Yeah, I'm reading it. So the decoder predicts the next word knowing the meaning of the input by looking at the word it predicted earlier. Yes. So it takes two things as input. The whole context of I love learning in this example. So the English version, I love learning gets embedded. That's your context. The decoder is going to take as input that context along with the words that were predicted before. So that's a translation example. Going back to my other example of GPT summarizing something, it predicts one word at a time. Every word it predicts, it uses what it predicted before, along with the instruction that you gave it. And the instructions that you gave it was summarize my essay. So it takes everything into consideration. And every word it predicts, whenever it predicts the next word, it adds a new word to the context. I hope that answers your question. I see that there's other question that does this concept works with numerical topics or only with text and LLMs? What do you mean by numerical topics?
Maybe the case that you were talking about, where we need to calculate the return of an investment.
I see what you mean. Yeah, this also applies to other other use cases where text is not necessarily the inputs. And for example, you have generative models that generate images, but you also have models like Time GPT that are used to predict time series. So they are trained on lots and lots of time series. And so if you give it, for example, let's say you have the price of Apple up to today, then it would be able, well, I don't want to say it would be able, but the task it will address is to generate the future returns or the future prices of Apple. So you do have those time series version of models. But what we're going to see mainly in this course is really working with text, because text up to a year or 2 years ago, it was very hard to extract the information in this type of input. And if you think about the financial industry, that's really like untapped knowledge and untapped information. There's just a lot of text in finance. And That's why generative AI has been so transformative in that space, because it's like all of this knowledge that we couldn't really use efficiently before, now we can, basically. And I see that
Okay.
there's another question. In order to generate good encodings as output from unknown inputs like ChatGPT questions, the encoder decoder are previously trained, right? Absolutely. Yeah. So all the models that exist out there, like Claude, like ChatGPT, like Mistral, this just every day feels like there's a new model that comes out. They are pre-trained. So it's like some form of transformer architecture that has been trained on lots and lots and lots of data. And then what we do is we take that model that's been trained and we use it as is, and we just give it instructions. Okay, so one thing I didn't say is that in the architecture of a transformer, there's encoder and decoder part. But in reality, if you go read the Attention is All You Need paper, it's really 6 encoders and 6 decoders that are stacked on top of one another. Why 6? You can go read the paper. They tried different numbers of encoders, decoders, and 6 was the one that worked the best. But BERT and GPT are 2 very notorious models that do different things. BERT is an embedding model, right? It's the classic example. Whenever you want to take text, convert it to a numerical version, you're going to use BERT. And BERT is essentially all of the encoders of the 6 encoders of a transformer that are stacked on top of one another is what you would use to transform text to numerical values. So in a nutshell, it's really taking this part, this part. You have your sentence, you pass it through your encoders, you get the numerical version. That's BERT. Okay. GPT is the decoder part. So if you stack all of your decoders on top of one another, you have a generative model. It takes something as input, instructions, more text, and then it just predicts the next word. Okay, so I want to wrap up the theory in the next 5 minutes so that we have enough time to go over the tutorial. So I'm going to go very quickly on over the different parts of the transformer architecture, and then we'll transition to the tutorial. So as I said, encoded decoder, we have actually 6 of them in a transformer architecture. But every encoder has the same components. The encoder is going to have what we call a multi-head attention. And then following that, it's going to have like a classic feed-forward neural network, whereas the decoder part has 2 multi-heads and a feed-forward. The way this would work is that if you have a sentence like "I love large language models," every word goes into your multi-head attention at once. So that's why it can sort of be parallelized, because all the words are sort of going into your architecture at the same time. And then they will be compared to one another. And the output of that will be inputted into the feed-forward component of the architecture. One thing that happens though is that whenever you're passing your sentence into your multi-head, so as I said, every word is going in the multi-head at the same time. So you're losing track of the order of the words. So a key aspect of transformers is that, yes, every word is inputted at the same time and they are compared to one another, but there's a key component which we call the positional encoding. And I'm not going to go into the details of it, but positional encoding is basically like adding something to every word so that you don't lose track of the order of the words in your sentence. It just keeps a vague idea of the position of the words in your sentence. Last bit is the output of your architecture, which always ends with a softmax function. Okay, a softmax is just a function that assigns a probability to every word in your vocabulary. So the word that gets predicted is the one that was assigned the highest probability. So if you have something like the sky is, there's many answers that are possible. It could be blue, it could be clear, it could be cloudy, but depending on the context that came before in your sentence, there's going to be one word that's going to have a higher probability. I'm going to skip because I'm going to make sure that we have enough time. I'm going to skip the other components. If you want to read the article, you can get more information there. So let's just very quickly finish on a round of questions, just to recap what we just saw. What is the main difference between GPT and BERT? Again, you can use the chat to answer. Yeah, so you all got it right. I should make my questions a lot harder. So GPT focuses on generating text, while BERT focuses on understanding language. What is the cosine similarity used in the context of word embeddings? So the answer is C, but honestly, if you would answer A, I think that would be also a good answer because they kind of mean a little bit the same thing. So cosine similarity sort of measures how words are similar. And it's sort of a measure of the distance between words in the context, the whole context that they were embedded in. All right, so we have exactly 30 minutes to go over a tutorial. And the tutorial that I prepared for today's session is... Okay, just give me... Okay. We're going to talk about crypto news sentiment analysis and NLP signals. So I work in finance, and my role as a director of data science is, so my team does two things. The first thing is to develop some agentic capabilities for investment teams. So if they have a question, they can go ask the agents that we develop. And the other component is to build signals. Now, a signal is not always a well understood concept, but the idea behind a signal is that it's supposed to help you make some investment decisions. And how exactly does it help you do that? So if you have one asset, like Apple could be a potential asset. It could be any company that is traded on the stock market. It could be a cryptocurrency. It could be, real estate. It could be infrastructure. But every asset at any point in time, you want to be able to make a decision. Should I invest? Should I not invest? This is what a signal is supposed to give you as information. Today, I wake up. Should I buy Apple? Should I continue being invested in Apple, or should I sell Apple? And so what I want to show you in the next 30 minutes is the process of building signals and the process of building very specific signals using text, because that's a new thing. We couldn't do that 2 years ago, and now we can. And we can do that using embeddings, using transformers, and using sentiment analysis. So the data set that we're going to work with is a crypto news data set. We have about 12,000 articles over the span of a year. So that's more than 1,000. That's more than 100 per day. That's more than 300 per day on average. So it's quite a lot of information that we can use to build signals. So the first thing is we need to install some libraries. And before I get into the details of the notebook, I just want to say that I am not going to share the notebook in Canvas. The session is recorded, so you can always go back and watch it, but I'm not sharing the code. So, and whatever we're going to see here is some of the things that you're going to have to do in the course projects. So, quite important information. Okay, so the libraries that we need are obviously sentence transformers because we're working with text. We're also going to use LangChain and FES because we're going to create a database of embeddings that we're going to use to create the signals. The data set that we have is a crypto news. So every row is one news article. It contains a date and it contains other information as well. The sentiment model that I'm going to use here is a already pre-trained classifier for sentiment, and it's called FinBERT. So it's basically a BERT model, an embedding model, but that's been fine-tuned on financial data. So it's a little bit more specialized to this type of text. And this model is available. It's an open source model that you can have access to in Hugging Face. So what I'm doing here is I'm just creating a classifier instance using my FinBERT model, and then I'm just testing it. I have a text here that says Bitcoin surged past 60K as investors reacted to positive ETF developments. So if I pass this sentence into my classifier, my sentiment analysis classifier, this is the output that I'm getting. So I have labeled positive, and it's 95-ish% certain that it's a positive news. So this is just to check that, because you have so many models on Hugging Face and they're not all good. Okay, so if ever you want to use open source embedding models, always check them, check the reviews, check the likings, and then also try to evaluate them in the as you're using them. Okay, so we know that it works on this sentence, but let's just run it on the entire data set. So that's the next thing I'm doing here. I'm just passing all of the news, so that's the text column in my data frame, into my sentiment analysis model, and I'm getting all of the labels and all of the scores. And then what I do is I just add it to the data frame. So the data frame looks like this. I have the date of the news that came out, the source, the subject, I have the text, I have the title of the article, I have the URL, and then I have the sentiment. I see somebody commented that now Bitcoin is at 120K. Yeah, so this is a data set that dates from a couple of years ago. Things have changed since then. So basically, I have all of this information, and then I just always like to have a look at the constitution of my data frame. So I like to use the describe function just to see, like, I know that there's 3 sources. I know that there's 6 subject, and I know that the one that comes more often is Bitcoin. About a third of the data set has a subject Bitcoin, but other subjects would be DeFi and blockchain and so on. So this is a nice quick function just to understand your data set a little bit better. So I want to build NLP signals, and I want to be able to build a signal that is going to tell me when I should invest in Bitcoin and when I should divest from Bitcoin. So what I'm going to do here is just filter my data frame on the subject Bitcoin, because this is really the asset that I'm concerned about. So once I do that, I have a little bit less news, but still quite a lot. Over the span of a year, I have almost 5,000. And then what I did is I always like to check a little bit like the distribution of certain columns. And in this case, specifically for the sentiment, I see that we have about the same proportion of neutral, negative, and positive. We have more neutral and then a little bit more negatives than positives. And I think this makes sense, and you're going to see why in a short moment. So we haven't talked about vector stores from a theoretical perspective. We're going to talk a little bit about it in the second active class, but for now, I'm going to still implement a vector store. The only thing you need to know about vector stores, if you're not already familiar with them, is that it's a database of embeddings. But it's very useful because you can query your database based on text. So it's a little bit like a Google search when you type something in the Google bar and then you get a list of results that are the most relevant to what you put as query. Vector databases allow you to do the same thing. So you put all of your text into that database, and then you can type a query, and you're going to retrieve the results that are the most similar to your query. Okay, so the embedding model that we're going to use is, again, a Hugging Face model in this case. I'm using All Mini LLM L6v2. This is a Hugging Face model. It's honestly one of my favorites. We use it at work all the time. We also use OpenAI embedding models, but this is a good embedding model that I recommend. And what I'm doing here is just testing my model. The next step is to create the database of all of the embeddings. So I want to take everything in my news and I want to embed it and store it. The first thing that we have to do is to create what we call the index. And the tool I'm using here is Fess, but there's just so many tools out there that you can use. There's Pinecone, there's Quadrant, honestly, there's more than I can name. This one is a easy one to use. So what I'm doing here is I'm creating my index. What is in the parentheses here is that I'm embedding a query, hello world. It could be anything. I could just put any sentence, any word. What I'm interested in here is just having the size of my embeddings, because that's what I need to pass to my index. Okay, so length, the function len, is giving me how many values do I have in my embeddings. And in the case of the model that we're using here, I believe it's 384. So I could just do this and it would be the same thing. Okay, so I created my index, and now I'm going to use this index and create my vector store instance. Once I run this, I have my vector store, but it's empty. There's nothing in it, but it's like I have the sort of shell of my vector store. And then the next step is we need to put something in it, right? Because we're going to need to query the information inside of this database. Before we do that, what's really nice about vector stores is it's a database of embeddings, but you can also add metadata along with your embeddings. So you could have the news article, but you could have along with it the date, the source, the sentiment. Why does that matter? It matters because then you can filter that database or that vector store on the metadata. Okay, so it allows you to extract subsets of that data set and then to query on that subset. Some of the information that I do care about is obviously the date. So I made like a little function that is going to transform the date format into a one that I want to use. Okay, so this is the part where we're basically transforming every news into a class called document. And again, here I'm using the LangChain library to do that. But I'm transforming every news article. It's a very long line of code. But I have the content of my news here. I have the source, the date, the sentiment. And what I'm doing is I'm just transforming it into a format that my face class understands. And I'm passing it the content and then the metadata that is associated with it. Once I do that conversion of every news article into a document class, then I can add it to the vector store. And that's what I'm doing here. Okay. So I have all of my documents that have the format that I need them to be in to fit the FES framework. And then I just add it. So once I run this line of code, I have a filled up vector store that I can query. Okay, so this is just the buildup that we need to create our signals. Now, how do we create the signals? Is the next question. I am a little bit familiar with crypto. I'm a lot more experienced with traditional finance. So what I did is I went on ChatGPT and I brainstormed with ChatGPT on what would be some interesting topics that could make nice signals for Bitcoin. And these are the suggestions that GPT gave me that I thought were interesting. The first one is everything that has to do with regulation and legal actions. And that makes sense, even in traditional finance. If you have a company like Apple and tomorrow there's a news that comes out that there's like a big lawsuit against Apple, most likely the stock's going to go down because that's like a very negative event. On the other hand, if you have like a new law that comes out that favors a certain industry, the stock price is going to go up. So it's the same thing with Bitcoin. Regulation and legal actions against the cryptocurrencies is going to affect how they move in the market. Second one that I thought was really interesting that was suggested was everything that has to do with partnerships. So whenever you have something in the news that comes out that says, I don't know, like this country, Mexico, the Bank of Mexico, this is not true, by the way, but let's say tomorrow you have a news that says the Bank of Mexico is going to start using Bitcoin. Well, probably the Bitcoin price is going to go up because that's like the announcement of a partnership and the announcement of an endorsement of a well-known organization. And that's a very positive signal. And then we have the same thing for security breaches obviously very negative. And then adoption of cryptocurrency by major institutions. That's this one is very similar to the second one. Okay, so these are very specific topics that we know can signal negative or positive. So what we want to do is to design a query for each of those topics. And then for each of those query, we're going to have 3 different signals: positive, neutral, and negative. And then we want to basically see, is there a pattern between those signals and the price of the asset? Okay, so what we're really trying to do here is we want a time series. Okay, we want a signal every day. And we want to see, is there like a pattern, a correlation between the price of the asset and the signals? So that's the query, very simplistic query that I'm designing for the first topic on regulation. So I just typed government policy, regulation, legal action related to cryptocurrencies. And what I'm doing here is it's kind of, think of it as a Google search. So I have my vector store, and I want to retrieve all the news that are closest to this topic. I want to retrieve the top 2000. Obviously, this is really high. I'm not expecting 2000 news articles to be relevant, but just for the sake of the exercise, I put the number really high. I see that there's a question in the chat. Why are we using a vector store? Is it to compute the embeddings of the articles only once and store them for future reference? Exactly. Yeah. That's the reason why you would want to have a vector store. A vector store is really something that lives. Okay, so if you only wanted to use the embeddings once, it wouldn't really make sense to use a vector store. But here is like, we know we have all of this content that we can leverage many times. And so it makes sense to store it into a separate space. Where was I? Okay, so I retrieved the top 2000, but then I know that it's probably not 2000 that is relevant, so I want to set up a threshold. And the threshold is based on the similarity between the similarity or the distance depending on the measure that you're using. So I want to really isolate the news articles that are the closest to my query. And this is what I'm doing here. Okay, and I think I have the output here, which is a time series for my first signal on regulation. So how do we interpret this? This would mean that on the 5th of November 2021, we had one news article that was neutral about regulation. We had none that was negative, and we had none that was positive. And if I go down the list a little bit, about a year later, we had 2 negatives, 2 neutrals, and then 0 positive. Okay, so you see how I'm taking news that is dated, and I'm transforming that into positive, neutral, and negative signals about a specific topic. Okay, the next step is like, okay, let's say I want to scale this and I want to try many different topics. I think there's a question, how do you decide the threshold? It's a very, very good question. So the 1.17 here it's somewhat arbitrary, but I tested it. So what I did is I did a couple iterations of like printing out making some queries and looking at the results, and then just going down the list, and I saw that 1.17 seemed to be where, the results would start not being relevant. But and actually in real life, it really depends on your use cases. If you want to be very strict about the relevance of the documents that you retrieve, then you could increase or decrease your threshold accordingly. we have about 9 minutes left, so I want to make sure that we go through the whole notebook. What I'm doing at this point is I'm just creating a function that repeats everything we did before, but so that I can just replicate it. I can create new signals. Okay, so the function is called create NLP signal, and one of the arguments is the query. Okay, so it's the topic that you want to extract. And then the top K, your threshold, and then if you want to give a name to your signal. What I'm going to do is just use this function with every different topic that we talked about earlier. So the regulation was one of them, partnerships, security, and then adoption, and then the general sentiment around BTC. Okay, so regulation, I'm using my create NLP and I pass my query, and then I have a time series. I do the same thing for partnerships. So here the query is partnerships, integration between cryptocurrency projects and established companies. And then I have an output, which is a time series. And then my third one is security breaches. The query is security breaches, hacks on cryptocurrency exchanges or wallets. So I have my time series. Fourth one is adoption by major institutions. I have my query over here, acceptance, adoption of cryptocurrencies by major companies or financials. I have another time series for that. Okay, so you see the process just repeats itself, and we could design as many NLP signals on different topics as we wished. The last one is I just want to extract whatever is relevant to Bitcoin at this point. So I have 5 data frame at this point with time series that is topic related and that is classified according to the sentiment labels. So if I take all of these data frames and I just combine them all together, I end up with this data frame that has overall 15 different signals, right? Because I have 5 topics and I have 3 sentiment labels for each. Okay, so let's dig into a little bit of visualizations just to see how can we observe any patterns. And what I'm doing here is I just want to plot the date and the number of negative, neutral, positive articles that we had for every topic. And what we end up having is something that looks like this. So the first topic is regulation. And what we're seeing is there seems to be 3 peaks. One in February, one in June-ish, and one around August or September for the negatives. And then if I keep going down, we have a smaller peak for partnerships around the same dates for negatives again. And if I go down a little bit more, we have a peak for security around August-ish. And if I go down, okay, I have BTC here. I see that there's a peak around February, and then April, and then June, and then August. Okay, so it could also be related to the number of news that are coming out on those days that make the number increase. So a good idea would be to normalize the counts that we get, but just for the sake of this exercise, what I really want to show you is how you take text and you convert that into financial signals. One thing that is missing at this point is that we don't really know how BTC performed during that period of time. So what I'm doing next is I'm just using the Y Finance library and I'm pulling out the historical prices of BTC for the same period. And then I'm plotting that, and it was a really bad year for BTC. It went from 70K down to 20-ish K. So it lost like 75% of its value. See that we only have 4 minutes left, so I'm gonna try to be as quick as possible. So the next step is just to compare the signals and overlay that with the price of BTC to see if there's any pattern. Okay. Obviously, if we wanted to really determine if these are good signals in real life, like the job that I do in my team, 1 year is not enough. Okay, we would expect to have at least 10 years so that we can really back test the results and see if there's like an actual connection between the signal and the price or the return of the asset. What I'm observing in these graphs is nothing that I can absolutely with certainty confirm that there's a relationship. And what I would need to do next is probably use a predictive model and to see if I try to predict the price of BTC with and without the signal, do I see an improvement? And then that would be a confirmation of the value of these signals. I'm going to conclude on the last bit here. What I ended up doing is I said, okay, so what if we simplify and we just remove the topic component, and for every given date, we just look at the proportion of positive, negative, and neutral news. So on a given day, if I take the last 7 days, did I have more negative or positive news that came out? Because that seems like a very logical signal. But what I did is I just created a function that gives me that proportion on every given day. And I'm just scrolling here. Okay, and I ended up with this chart here. So in black is my BTC price, and in red is the proportion of negative news. In green is the proportion of positive, and then in gray is the neutrals. So what I am seeing, again, it's just 1 year, but what I am seeing is there seems to be a little bit of an upward trend in the proportion of negatives. And that's kind of makes sense when you see the price that is going down and down and down. But again, we would need to study it a lot further to confirm that there's an actual pattern. So I'm gonna leave it to this for today. It's quite a lot of information that I just gave you. In the next 2 weeks, you're gonna have your first course project that is going to be related to the topics that we talked today in the tutorial and from a theoretical perspective. And you're also gonna have a quiz that is due, I believe, next week. So if there's a last question, I can take it. I see that there's a question. Is this a fundamental analysis example? It depends what you mean by fundamental. For me, fundamental means something different. It means something more about analyzing an asset from a qualitative perspective, not so much from a quantitative perspective.
And I think there is another question before. Is this how do you decide
Oh, no, I answered that.
Okay.
Already. I see there's another one. Can we access the news CSV to practice? I can share the news CSV. I can do that. I can post it on Canvas. So thank you, everyone. I see there's a last question, and then we'll have to conclude.
Yes, I was just curious about because I was doing my portfolio with not cryptocurrencies, but currencies. For example, USD and Mexican peso.
Yeah.
And my question is, when the Fed has its monthly meeting, they publish this PDF.
Yeah.
Can we use this PDF to start making this sentiment analysis based on the stock currency?
Yes. Absolutely.
Yes. Wow.
Absolutely. And the reason why I'm laughing is because I worked on this exact use case in the last year. And what we do is we scrape the Fed website and then we quantify the documents into what we call an OCDOV score to determine how likely the Fed is to increase or decrease the interest rates. So, it works really well. Yeah.
Wow! And also, just the last one. This apply it can be applied the same for if I want to make my portfolio about clean energy companies, right? When they publish their financial statement.
Yep. You could do that on the financial statements, but you could also do that on the earnings calls. So that's public information. Whenever, like every quarter of the year, every company that is publicly traded, they publish an earnings calls, and you have access to the transcript of that on their website. So that's very valuable information that you can use with sentiment analysis, and you can do all kinds of very fun signals with that.
Wow, thank you.
Thank you so much, everyone. Have a very good evening, and I'll see you on the 28th of July.
Merci beaucoup, Marie-Ève.
Merci. Bonne soirée.
Bonne soirée.
Thank you.
Thank you, teacher.
One more question in the
See you
chat.
later.
Where could we find the notebook mentioned for? Is it going to be available next week? The one for the homework or project? Sorry.
It should already be in the canvas in the
Okay.
course project part 1.
Yep. Yeah, that's the one.
Yeah, it should already be there.
Okay. Thank you.
Somebody is saying it's missing, but we'll check and we'll make sure that it's there.
Thanks a lot.
Awesome.
Okay.
Thank you.
Have a good night.
Have a great day. Thank you. Bye-bye.
Thank you.